Thank you very much for the introduction. And I thank the organizer for the invitation. And I'm really grateful to be here and to have an opportunity to give a talk in this prestigious conference. And moreover, I'm really happy on this poster, which is really beautiful and has a lot of Dutch flavor. So it's really beautiful now. I'm really happy with that. So today I'm going to talk about the regular Poisson structure, namely codimension 1 foliation on the 5 sphere, which admits a leaf-wise symplectic structure. So I'm going to show you a construction, and my talk is going to be, I think, it's going to be quite geometric and explicit. So, and about this subject, there are several points of view. So this might be interesting from the point of view of the story about Lawson's foliation, and also the core part of the construction has a lot to do with the pseudo-convexity, and in some sense I have to break the pseudo-convexity in the sense of symplectic structures. So that is the really core part of the construction. So this story is in some sense interesting from that kind of point of view in complex analysis. And also this is also related to the existence of a foliation associated with open book decomposition or Milnor fibration of some singularity, and convergence of contact structures into that foliation. And that is also another good point of view to look at this subject. So today maybe I will concentrate myself on the second and third points of view. And of course I mentioned something about the first one. So let me start. And here is the plan of my talk. Introduction. I will talk about some brief history on Lawson's foliation, and then blah 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 blah. And I don't believe I can arrive until the end. But anyhow, let me start. So first I will state the result. So here are well-known three kind of polynomials. They define in 3 variables, in 3 complex variables, and they define an isolated singularity at the origin. And the first one is the third order homogeneous. The other 2 are also. Thank you. Yeah, thank you.
Middle button.
E to 6, this is a cubic, Feldman type cubic polynomial, and E to 7, E to 8, they are not homogeneous, but they are of weighted homogeneous, so they are not difficult to treat with. And the first term, theorem A, states, claims that not taking 0, but taking the inverse image of 1 or any regular value, it defines a Feldman cubic surface, affine surface, and of course this affine surface carries a natural symplectic structure, but it's really expanding on the end. But we can modify the symplectic structure on that surface in such a way that the end admits the symplectic structure on the end is somehow periodic. So this is the real part of my theorem. And the same applies to the other 2 polynomials, E to 7 and E to 8. If you take these inverse image of the regular values, then those affine surfaces also admit symplectic structures which are periodic in its end. And so in two variables case, so it's really easy to construct a foliation which is associated to the Milnor fibration. Or if you have an open book decomposition of three manifold, then it's really easy to associate a foliation to the open book decomposition, because the binding is only a circle, and if you put tubular, the so-called web component on its tubular neighborhood, the tubular neighborhood of the binding, then you can construct quite easily a foliation associated with that open book decomposition, and even you can show that the associated contact structure converges into that foliation in a family. And but in higher dimensional case, it is highly non-trivial to construct such foliation. And for those three polynomials and the Milnor fibrations for these singularities, it is known that quite easily we can associate a foliation. That is the real part of the Lawson's work in around 70. And so we have foliations. We have foliations associated those singularities. Then, from the theorem A, with a little bit of work, we can prove that, for example, the Lawson's foliation, which is, I'm sorry, it goes to the, in E60 case, the associated foliation is what we call Lawson's foliation. And for those foliations, we can show that there exists a Li-Phi symplectic structure. Namely, there exists a regular Poisson structure with symplectic foliation, associated symplectic foliation of dimension 4, which coincides as a foliation, which they coincide. It coincides with Lawson's foliation, and the same applies to the other two polynomials. This is the result to explain today. And okay, here's the definition of Li-Phi symplectic structure. Namely, the Li-Phi symplectic structure is a smooth two form which restricts to symplectic forms on each leaves. And that is the same thing to say that I'm sorry. This is in the parenthesis, and it's the same thing to say that there is a smooth cross section to the second exterior power of the cotangent bundle, and which restricts the symplectic form on each leaf. That's the same, almost the same thing. And because to take a, so in above definition we take a cross section to that Doran complex of leaves, and to go down to the definition in parentheses you have to take a lift. So there are a lot of choices to take a lift, but it's not a important point. And so this is really equivalent to say that there exists a regular Poisson structure. Okay. And no. Forget about this part. So a little bit history about Lawson's foliation. So as I told you, on F3 or a three-dimensional case, it's really easy to construct foliation associated to some singularities or open book decomposition, because you have, as you know, on D2 cross S1, namely on solid torus, there is a famous foliation which is called, which we call Leb foliation or Leb component. Which looks like this. And of course, the boundary torus is a compact leaf. And if you prepare two of them and paste them to glue, then you get a famous Leb foliation on the free sphere. And but if you have an open book decomposition on five manifold, so it's a bit difficult to put a simple foliation like that on the tubular neighborhood of the binding. So the binding is not so simple in general. So to construct a codimension 1 foliation on S5 on the 5 sphere, it was not so easy problem around 1970. So Lawson constructed such foliation. That was, I believe, that was the first one found on S5. And the interesting point of this foliation is, like in the case of Leb foliation, the foliation itself is really simple. They have two components and one common boundary, and the common boundary is a compact leaf. That is only the unique compact leaf. And the compact leaf is so-called Kodaira-Thurston's new manifold. And the interesting point is that it's not Kera, because the first bit number is 3, it's an odd number. So the manifold is known to be non-Kera but symplectic, or non-Kera but complex. So it's an interesting compact leaf. So here is the Verzhovsky's question. So he asks the following questions. Does there exist a leaf-as complex structure or a leaf-as symplectic structure on Lawson's foliation? Or if it is difficult, you can modify a little bit foliation, and still we can ask the existence of such structures. And because as I told you, the common boundary is Kodaira-Thurston new manifold, which is not Kera. If the answer is yes for both questions, you cannot solve them by only one example. So you need two different examples to say yes for both. But I think I don't believe that the complex structure exists. So today I show that really the symplectic structure does exist for Lawson's foliation without any modification. And the interesting point is that, as I told you, you will see that there are two components with one common boundary, and so one is the tubular neighborhood, the other one is really filled with Fermat-cubic surfaces. And on that part, Fermat-cubic part, in fact, it is really easy to put a complex structure, leaf-as complex structure. But for symplectic structure, that is really the difficult point. On the other hand, if you look at the tube component, namely the tubular neighborhood of the binding, then it is really difficult to put complex structure, and people believe that it is impossible. And for that part, on the other hand, to show the existence of symplectic structure, leaf-as symplectic structure is very easy. So for the complex problem and symplectic problem, the difficulty on this part component, on that component, it is converse to each other. That is interesting point. Anyhow, so the most of the work should be concentrated to understand what is Lawson foliation, how it looks like, how their leaves looks like. That is all thing that we have to do. So let's take a close look at the Lawson foliation. So here is a polynomial again. And capital FW is the level surface, the inverse image of the regular value W. And so if you multiply some constant lambda, then FW is sent into FC cube W. So every leaves every regular surfaces are diffeomorphic or complex analytically the same, except for the singular fiber. Okay. So now let's look at the Milnor fibration of this isolated singularity. So you cut by the unit sphere. So as this is cubic homogeneous polynomial, so you can take any sphere of any radius. That's the same thing. So let's take a unit sphere, and the Milnor fibration is defined on the S5 minus the F0 and singular surface, and the fibration is defined by taking the composition of the function f composed with taking the argument of the complex value. That is not in the Milnor fibration. And the important point is that here is the picture. Here is F0, so this is the singular surface, and take the intersection with the 5 sphere, and then here we have the intersection, which is S5, intersection with S5 and F0, and which is denoted by N, which is a new manifold of dimension 3 with Euler number minus 3. So, and I think it may be useful to look at this picture, pushing down to CP2 by Hopf fibration. Then the singular locus goes down to F0 goes down to an elliptic curve, because it's a cubic polynomial, so it defines an elliptic curve in CP2, and because of the polynomial is of degree 3, so that link is nothing but the circle boundary over that elliptic curve with Euler number minus 3. Okay. So here is the fact. All right. So this is the first thing to understand. So N is the first Chern number minus 3, and but still we can go down. So this is an important point. So still we can go down. So here is we have a T2, and we give coordinate x and y. So we go down to one circle of x coordinate. Then we get what we get is T2 bundle over the circle, and then the coordinate y goes upstairs, and also because this has a non-trivial curvature, so zeta, by zeta I denote the canonical connection form for this Hopf fibration, and once it is restricted to this elliptic curve, so this is denoted by zeta n, sub n, and this is not a closed form, but anyhow we have two coordinates here and one coordinate x here, and this is a T2 bundle over a circle with that kind of monodromy. So this is the structure of the link of the singularity. And is it all right so far? Now, if you look at this picture of wave component, it is so difficult to construct Lawson's foliation. So let's take a tubular neighborhood W of the link N in the 5 sphere. Okay, the W is the tubular neighborhood of the link N in S5. So N is 3-dimensional. S5 is of course 5-dimensional, and it's coordination too. But as you can see by the function small f, the original function small f, the tubular neighborhood is trivialized by the value of function f. So on S5, only on N, f takes value 0. Okay, in a normal direction, the small f really trivialize the tubular neighborhood. Therefore, the tubular neighborhood W is diffeomorphic to D2 cross N. All right. So if you look at the structure of W, then we can say that it's because N is T2 bundle over S1 with that monodromy. So W is tubular neighborhood is a D2 cross N, and which is diffeomorphic to T2 bundle over D2 cross S1. And if you go around S1 direction once, then simply the T2 have a monodromy like that. All right. Then you can see that. So as already we have prepared a wave component on D2 cross S1 on downstairs, and simply if you pull back that foliation, wave component foliation to the tubular neighborhood, you can see that it's easy to, we have a coordination 1 foliation on that tubular neighborhood with a compact boundary, compact leaf as a boundary. Is it all right? And this construction will tell you that there is a symplectic structure on that tube component. Anyway, okay, and so we could foliate. We have foliated a tubular neighborhood of the tubular neighborhood of the binder, but the other pass on the complement. So we have to look at the fibers of Milnor fibrations. The Milnor fibration has a simple structure in this case. So let me explain that. As written in that transparency. So on S5, here is N, and in some sense N is going like this, and here is the tubular neighborhood, and other Milnor fibers are coming like this. So if you fix an argument theta in complex number, then I call it lambda theta. So Milnor fiber associated with this argument comes like this, and this is on the picture. This is the picture on S5, but if you look at C3, so here maybe it's better to draw in this picture. So if you take F0 like this, F0 is really like a cone, but for example, F1 is going like this, and on the end, F1 is really approaching to F0 and getting closer and closer at the end. So the end of F1 and end of F0, they are almost the same. And not only that, if you carefully compute, so for example, if we take F1, so the argument, corresponding argument is 0, and simply if you project F1 to S5 by dividing by its absolute value, then F1 and lambda 0 correspond to 1 to 1 to each other, so they are diffeomorphic. And that is one important point. So, in general, FW is diffeomorphic to the Milnor fiber of argument W. That is the important point in this foliation. So each Milnor fiber is the same as the affine surface. And also, if we go down to CP2, the locus is the elliptic curve, so we remove it. Then these two, F1 or lambda 0 or any FW or Milnor fiber goes down here as a triple covering. It's a regular triple covering. Is this all right? So if you look at the polynomial and compute the value and carefully think about the scalar multiplication, you will see those facts quite easily. Okay, this is a really nice property of this cubic polynomial, and thanks to these properties, the construction can be made very, very geometrically and explicitly. Okay, so now we have a Milnor fibration description of the Milnor fibration, and somehow we can foliate the tubular neighborhood of the binding. But the next step is to foliate the exterior of the tubular neighborhood. But that is really easy, and maybe it's better to write here. So if you look at this picture, then again I will draw the same thing, but now I draw the link N as a point, all right? And here is the transverse section of the tubular neighborhood N, W. So one Milnor fiber comes like this, the other Milnor fibers are coming like this. And to foliate this structure, this space, it's easy to modify this picture into this one. So this process is called so-called turbulization in the world of foliations. So simply, if the Milnor fiber approaches to the tubular neighborhood, then simply you rotate it. Then this becomes a compact leaf. The inside, in some sense, the inside the tubular neighborhood is foliated exactly in the same way. But in that case, for tubular neighborhood, so this rotational direction is not in this direction, but in some direction inside N. So in this direction, if you turbularize it, then you get this one. So in some sense, two components are foliated in the same reason, but in different directions. And this is a construction. So you can see that each leaf which sits outside the tubular neighbor is diffeomorphic, and also they are diffeomorphic to the thermocubic surface. So the exterior component is foliated by the thermocubic surfaces. On the other hand, inside we have a pullback foliation from here. That is the structure of Lawson's foliation. So already we have foliated the 5-sphere in this way. And coming back to the history about foliating S5, so soon later, no, it's not here. In 77, I think, Poisson proved the H principle for the codimension 1 foliation. So if you know that the manifold has trivial order characteristic, Poisson showed that it admits a codimension 1 foliation. And in this case, relative version really works, and simply computing that the tubular neighborhood has also trivial Euler number as well as its boundary. So we can foliate, and there exists a foliation on tubular neighborhood or the exterior component with the boundary compact leaf. But if you use the Poisson's H principle, then you cannot see the foliation. It's really complicated, and you have a bunch of compact leaves, and it's really, usually it becomes a really ugly foliation. So in some sense, I started to study foliations after Poisson's H principle, and around that moment I didn't pay much attention on the Lawson's foliation, because the existence is already simple query of Poisson H principle. But now we see that the original construction of Lawson's foliation. So if we look at Lawson's foliation, it has a rich geometric structure, and it has a lot of interesting properties to work on still. So that is the end of the history of Lawson's foliation in my talk. So next, let's look at the symplectic structure. And first, I briefly explained that the foliation on the tube component quite easily admits defies symplectic structure. So to do that, maybe there is here, okay. So as I explained, zeta denotes the canonical connection 1 form for the Hopf vibration, and zeta n is the restriction over n. And on the elliptical, we gave a coordinate x and y quite in a topological way, and if you compute the curvature of zeta n, if I'm right, d of zeta n is in that form. So 3 pi times a half of 3 pi times dx wedge dy, and so that you can see that if you take a canonical area form for fibers in the tubular neighborhood, please look at the top. So the tubular neighborhood has this structure. So it's a T2 bundle over a solid torus. And if you put a canonical area form for D2, a T2 for this fiber, it's dy wedge. Where is the dy wedge zeta n? Okay, and it is a closed form, because if you take d of zeta n, so it contains a dy component. So dy zeta n is a closed to form. So that dy wedge zeta n is defined on W as a closed to form, which restricts to each fiber as a natural area form, which is preserved by the monodromy. Monodromy is area preserving. So already we have a nice two form. Nice two form over like this on W, and also we have so then the next step is to look at this rev component. So this rev component has, if you carefully look at the construction, what is the chalk? Yeah. This S1 has a x coordinate, and this D2 has D2 sits in the complex plane. This is the complex plane where the function f takes value, and so I will give a polar coordinate r and theta. In that sense, this boundary torus has a theta coordinate and x coordinate in this direction. So now, if you look at that rev component again, it's not difficult, and in fact it's very easy to put our two form on this rev component, which restricts to each leaves as an area form, and on boundary that restricts to dx, d theta dx. So it's very easy to put two form. This rev component admits d-phi symplectic form, and on the boundary it is written as d theta times dx. So we have that two form here, and it is pulled back to the tubular neighborhood. And also we have close two form dy zeta n. And if you take the combination, if you take the sum of them, linear combination with constant lambda and the coefficient lambda and mu, and if both are not equal to 0, then it gives you d-phi symplectic form on the tube component, and on the boundary it is written in that way, and that is the, so this is the end of the construction for symplectic forms on d-phi symplectic form for tube component. So the boundary of the tubular neighborhood is, so because the tubular neighborhood is d2 cross n, so the boundary is S1 times the new manifold, and this S1 has coordinate theta, this new manifold has x, rather d theta, dx, dy, and zeta n. They have those one forms, and this is the Kodaira-Thurston new manifold, and it admits a symplectic form like this, like in the number 2. Right. So we have constructed a d-phi symplectic form on the tube component, which restricts to this one, and we have a free choose for lambda and mu on the Kodaira-Thurston boundary leaf. Okay, is it all right? So this talk is really geometric and explicit, so you have to understand everything. So if you get lost, please ask me. don't hesitate. Now here is a really interesting point of view. So the reason why we could foliate the tubular neighborhood, we could easily foliate the tubular neighborhood, is that this link of the singularity, the new manifold, fibers over a circle. So that's the same thing that the Leb component, fibers over the circle, namely fibers over the X circle. And the tabularization is done with respect to that S1 direction. And here is there is a coincidence of the condition, this condition, namely fibering over the circle. That is really important, because there is a generalized interpretation of generalization of the interpretation why the Kodaira-Thurston new manifold admits a symplectic structure. So that is called beforehand we call it Talbot's conjecture. Now it's a theorem of Friedel and Bidusi. And if you take a closed four manifold, which is a product of the circle and some closed three manifold, and such a closed four manifold admits a symplectic structure if and only if that three manifold fibers over the circle. Then in that case, we can easily construct one symplectic structure. That is what we use already. So namely, if it fibers over the circle, then you have a fiber which is a surface, and any monodromy is realized as an area preserving diffeomorphism. So take that one. In our case, that is dy zeta n. And then take so we give theta to this circle, and to this circle and that circle are different. So this is, in our context, this is a theta circle, and this one is x circle. So there are so many circles, so it's really confusing, but it's a really, really important point. So n fibers over three manifold fibers over the circle. This is the x circle for us, and then take dx d theta, d theta dx. And already we have our area form coming from this fibration. And the area form gives you the area of fibers. Then the same construction gives you the symplectic structure on this four manifold. And there is a slight generalization in a higher dimensional case. If you have an odd dimensional manifold which fibers over a circle with the symplectic fiber and the monodromy, and if we assume that the monodromy preserves the symplectic structure, then that odd dimensional manifold times S1 admits a symplectic structure. We can do the same construction for the symplectic structure. So this might be interesting if we would like to do the same thing on the higher dimensional case. Okay, so the fact that the link fibers over the circle, that property is really important. One, for the easy construction of the foliation. That is the Lawson found, and the reason why the Lawson constructed the foliation in easy way. That is really the fact that the link fibers over the circle. And on the other hand, it also works for the existence of symplectic structure on the boundary leaf. So this property doubly works well for this property. Okay. Now I have to be quick. Now let's get into the real problem. So here is a natural symplectic structure on this C3, and it's written in that form, dxj, dyj, and it's also written in that way. And here we have to be careful a little bit. So on the right hand side in the parenthesis, that is something is missing. Exterior derivative is missing, but the x dy minus y dx, that is a standard Liouville form on C3. But if you restrict that one on the unit sphere, that really gives you a canonical connection form for the Hopf vibration. But if you use polar coordinate, so let's take rho as the radius on C3, then using the polar coordinate, so this form is written as a rho square times of zeta. Is it all right? So it's not zeta, but rho square times of zeta. That is really important point. So rho square is nice, rather than rho square is really useful for us as a radial coordinate. And if you take this exterior derivative, exterior differential, then it gives you the standard contact symplectic structure. So this is nothing but the symplectization of the standard contact structure on S5. Then so if you look at, so as I told you, the end of F1 and the end of F0 are almost the same. So if you look at the end of F0, so the symplectic structure is written in this form. Simply we have to restrict zeta to zeta n, and we get a symplectic formula written in this way. So as using x and y, this x and y are coordinates given on the elliptic curve, and nothing to do with this xj, yj. In that coordinate, and for some reason, theta is replaced by tau. But anyway, tau is the log of rho square. So I made tau is the additive coordinate, and okay. So the natural symplectic structure on F0, on the end, it has this expression. But here is some tricky part of the construction. So if you look at, so as I told you, F0 and F1 has almost the same end, so you can re-embed F0 by slight perturbation, slight isotopy, so as to coincide with F1 on the end. And that process enables us to consider the end of F1 is exactly the same as end of F0 as a symplectic manifold. So and if you divide this picture by some homotopy, then F1 becomes like this, some homotopy, and that is nothing but the Kodaira-Thurston-Neal manifold. All right. So here is our F0. Here is our Fn. We have also a bunch of F pi theta. And if you look at this F1, so maybe removing 0 and the origin and divide by the homotopy, then what happens is that, I'm sorry, this is F0. Here is F0 divided by the homotopy. Then the other, for example, F1 is spiraling into F0, because if you divide this one this space by single homotopy. So this gives you this picture. And this picture is nothing but this picture. So look at that one, and that gives you the structure around here. That is a really tricky point, and you have to think. So the things are going around like this, but in that picture, things are going around this way. So if you can adjust the two pictures into the same image, then you will see much better the structure of the Lawson foliation. But by using that, so here already on a Kodaira Thurston leaf, we have a symplectic form, and then that means we need a symplectic form on F1 because it's each leaf of the ferrocubic component is diffeomorphic to F1, and if we have already some symplectic structure on this compact leaf, and F1 approaches to the compact leaf in this way, then F1 must admit somewhat asymptotically periodic symplectic structure, and that symplectic structure must be not like that, but I'm sorry. Wait, I can skip. Yeah. In this way. So this is the same expression of the symplectic structure which I gave on the Kodaira Thurston manifold, but theta is now replaced with tau for that reason. So tau is the radial coordinate in this case. So above we see that that is a natural symplectic structure coming from C3, which the end of F1 has, but we need a symplectic structure like that on F1. That is really the point. So the natural symplectic structure is, as I told you, it's the end of a Stein manifold or affine complex surface. It's really on the end. It's really expanding, but we really need a not expanding one, but periodic one. So this is this is a fight against the pseudo-convexity, strong pseudo-convexity. So I think it is not so often, and rather I believe it's really rare that the Stein surface or Stein manifold admits an n-periodic symplectic structure. It's usually expanding, but we have to replace that natural one with some periodic one. That is the real problem of this problem. Okay. So this is our problem. Okay. So what to do? No, slightly below. Yeah, starting from the upper one, we have to construct some symplectic structure which restricts to the lower one on its end, right? And if you restrict to the lower one on some, so the end is like this. So the end of the F1 is the same as the end of F0, and the end is n diffeomorphic to half line times n. And if you restrict our symplectic form to n, so the natural one is already it's an exact form. But what we need is not exact. It has a clear second cohomology. So, because dy zeta n presents a non-trivial cohomology. So we have to do something about that. And for the first term, I mean lambda d tau dx, that part is not difficult. So d tau is a radial coordinate, it's a function. So e tau d on the first line, e tau d tau is also exact form, and also d tau is modified with our hand, but that dy zeta n is really stubborn, and so if you perform some magic in front of the audience, you have to prepare some trick. So here is the trick. That kind. The trick is that to get dy zeta n, we use some cohomological argument. So we can. It is presented in that form. So this from Milnor fiber to the link n. So it's a restriction map, and it is surjective. So dy zeta n lives in the second cohomology of the link, and that dy zeta n extends to whole Fermat cubic surface. That is the point. And even in equivariant way, I mean this surface or this Milnor fibration has order 3 monodromy that is coming from the Hop fibration, Hop action, and even we can construct everything in equivariant monodromy invariant way. But anyhow, we can do it, and that trick is proved quite easily if we go down once more. I mean, if we go down to CP2 minus the elliptic curve. So simply, if you take the tubular neighborhood, the elliptic curve in CP2, that is denoted by V. And in this case, what we have to show is that the boundary of looking at the boundary of the tubular neighborhood of the elliptic curve V, that is again a nilpotent 3 manifold. And this claim goes down to this claim. I mean, the exterior of the elliptic curve, from the second cohomology to that of the boundary of the tubular neighborhood, that is surjective, and it's proved simply by Mayer-Beatrice argument. It's really easy. So this is an exercise for students. So it's really easy. For that simple reason, this is proved, and also this is proved. So that is the trick of the construction. And here is kappa, which is the extension of dy zeta n to whole surface in a monodromy invariant way. So now, once we get this one, we can finish the construction. So let me finish my talk with this construction. So it's really easy. So what we have is the e tau, some constant times the e tau d tau wedge dx plus some constant times dy. No, zeta n dx dy. And but this was d of e tau zeta n. So we replace this one with k of tau, and also what we need was some constant times lambda times d tau dx plus mu times of dy zeta n. This is what we want, and this is what we have. So we add something, with small constant mu, we add mu times of kappa. The kappa restricts to this dy zeta n on the end, and if you put really small constant, then it doesn't matter that for having symplectic form. So this is a symplectic form, and on the end, this has this presentation. So even if you compute the square of these two forms, even after we add this term, you see that dy wedge zeta cancels with, if you take the multiplication with this term or that term, it vanishes. It's a really magical trick, but it's really easy. So this, I think this one is has no problem on the end, but on the compact part, simply we have to take the mu small constant. So that is because of the compactness. Only that reason. This is a symplectic form again. Mu kappa. Then what we have to do is take a large enough constant t for tau, and replacing e tau with this. So up to certain certain radius, we take k of tau equal to e tau. Then simply we push down to 0. So we modify this function into this way, and instead we take another function, lambda or L of tau. So we replace this one with L tau, and you can see that still this is an exact form. And so what we have to do is to add all of them. So this is a construction, and as you can see, if you compute the square of this form, so these two terms gives you a positive volume. These two terms gives you also positive part, but here you have to be careful. But if the derivative of this L is much bigger than this one, this simply gives you a symplectic form, because these two parts and those two parts doesn't interact at all. That's the construction. And if you try to, if you put some more information on the cohomological argument, then you can modify everything into the leafwise symplectic form. But I think I have to stop my talk. So thank you very much.